next speaker, Alejandro, is going to tell us more about machine learning on quantum devices.
Okay, thank you. So it's a pleasure to be here. Thanks to the organizers for letting me talk about this work that I guess we decided to experiment about a year and a half ago. We really wanted to go into this to see what are the possibilities for quantum annealing for machine learning. So this work, the leading author in this work is Marcello Benedetti. He's now starting his PhD at UCL, so he came to NASA to start his master's degree. And it's also John Rialpi, who is also one of our research scientists, and Rupa Biswas. So let me get going, and let me just give you a contrast of where this work actually fits. And the very first thing, I mean, you're used to this type of formalism. I mean, the way I like to think of any quantum annealer or the D-wave is you can work in two modes, and they are complementary. So the very first mode is when I think of the D-wave of any quantum annealer working as an optimizer. So in that paradigm, basically, is the one that we've been working for about 10 years, trying to solve real-world applications on the device. And basically, what you provide to the device is the H's and the Jij's, and what you're expecting from the device is just to give you the lowest energy configuration. Basically, you're expecting a bit string that hopefully minimizes the energy. That's basically what we've been using for fault diagnosis. Have you seen lattice protein folding, any type of NASA application that we're interested in? The second paradigm is something that is a little bit different. And it's exactly when you are thinking of the device as a sampler, a device that you're going to use for sampling applications. So how is that different? So basically, with the way to think about this is now you're thinking that the device, instead of just solving a combinatorial optimization problem, is actually capable of giving you samples, reliably sampling from a Boltzmann distribution. That's precisely the talk right before mine. And here is the energy cost function. And as you can see, these two paradigms are not in disagreement. Of course, I mean, the assignment or the assignment with the minimal energy, of course, hopefully is going to have the largest weight. So basically, there was an early work in 2010 from the D-Wave focus actually pointing that, in principle, you could use the device to do this. But there was a little caveat. And it was actually, they realized that the device was indeed more or less consistently sampling from a Boltzmann distribution. That's precisely, I mean, and the physical understanding is partly, I mean, what Evgeny presented in my previous talk. So basically, there is a freeze out that actually you get to the classical point, and you can sample from the classical Boltzmann distribution. But the problem is this effective temperature. You really don't know what is the effective temperature. So if you're programming the device and you want to extract samples, you input the H's and J's, and you want to extract samples, the question is that there is no way you can know a priori what is the effective temperature. Why? Because this effective temperature is not related to the temperature of the device. It's related somehow, but it's not the temperature of the device. So basically, what that implies is what they show in that paper is that you basically need for each value of H, for every instance, you need to fit this parameter. And fitting this parameter actually is intractable. And therefore, you go in a circular argument that basically to solve the problem, you need to solve another intractable problem. So that's what our work is about. So of course, I mean, if you were able to do that, the potential is that you can explore models as the one as Evgeny was talking about. Here is, for example, a representation of a restricted Boltzmann machine that is just a probabilistic graphical model. This is the model we're going to focus here in this talk. And basically, when you have visible units, for instance, you can think as these units. They could be binary variables. For instance, imagine that you have a picture that is actually with binary variables. It could be a black and white type of picture. Basically, those are the ones where you're going to encode black, white. Those are the visible units. So those are the variables that are going to represent your data. In this probabilistic graphical model, the top layer is called the hidden units. They're basically just trying to capture correlations between the visible units. So why is this called a restricted Boltzmann machine? Notice the architecture here. There is no connections. In principle, you could put actually connections here, but there is no links. There are no links between the visible units, and there are no links between the hidden units. This is entirely an algorithmic construction in such a way that you can train this algorithm very efficiently. It's not actually, of course, I mean, if you had the opportunity to connect all to all, that would be great. But computer scientists realized that if you do this, you can move much faster, and you can actually make progress with contrasted divergence. That is the algorithm that they use state of the art. So you can think of this construction as an algorithmic, purely algorithmic and motivated. So there is still a caveat, even if you do this construction, and is that there is a computational bottleneck that is actually, that's why we're even in first place talking about why to use a quantum annealer, is the computational bottleneck is that when you are doing this, the training of this model, doing this stochastic gradient ascent, basically you need to calculate this type of correlations. V here stands for any of these visible variables. H stands for any of these other spins. So basically you need to calculate these correlations with the, notice that here this average is calculated over the full joint probability distribution. That's the difficult part. Because in reality, if you want to get samples or calculate averages over this model, that's again NP hard. So it seems like there is no way to make progress, but actually computer scientists came up with a good technique to do this. Now, of course, basically our proposal is that you could replace, if you had a way to get samples from the joint probability distribution, from the Boltzmann distribution of the full IC model, in principle, you can calculate and compute these averages and then do the training, hopefully more reliably than the state-of-the-art classical approaches. That's the promise. Basically, the very first thing that we tried in our very first work here is we really wanted to understand this feature of how do we efficiently compute this effective temperature. So I think there are two main contributions in that work. It's been in, the revisions has been accepted. It will be published in PRA soon. Basically, I think in that contribution, we provide an algorithm that robustly estimates the effective temperature. And by here, robustly, what I mean is actually, it's not that it's never going to fail. It's actually is that what it means is that it's the best that we can do compared to some other simple approaches that we tried in the last year before actually we came up with the final version of the algorithm. That's the most robust one that we came up with. And basically, the very nice thing about this approach, so this is the take-home message, is that actually you don't need to do any extra work. The same samples that you're extracting from the Boltzmann distribution to calculate the averages are the same samples that you're using to estimate the effective temperature. So actually, you get everything for free. You sample from the device, you get the samples, you compute the temperature, and then you can move on in the next step. So everything is actually, you recycle absolutely all the samples. So as actually, I just wanted to highlight there was a recent work from Dewey actually appeared a couple of months ago, a month ago actually within the last month, just actually emphasizing on the importance of this effective estimation of the temperature for this type of problems, for sampling applications. And then they were actually concentrating in this question. I think someone asked in the audience, what happens actually if you have a hard landscape? Will you get trapped in a local minima? Will you thermalize? All these questions, I think they were addressed a little bit more in detail in this type of, in this work. So that's the setting of our approach. And basically what I'm going to show you now is some of the results. So let me go first, give you in one slide what the algorithm is about. So the algorithm actually is very simple. From the many things that we tried, actually, this is the one that works the best. Is you have here your Boltzmann distribution. Here it is just the degeneracy, the density of states at a certain energy, and here is your Boltzmann's factor. We are only limited to the things that we can do with the device. So basically, what we have is that we can rescale, for instance, if I'm interested in sampling from the Boltzmann distribution at a certain reference parameters, H's and J, I'm allowed to rescale those parameters and come up with a new Boltzmann distribution. If I rescale those parameters, like here, just multiplying by x, basically what I'm doing is effectively changing the temperature. I can think as I have the same problem, but now with a different temperature. It's just basically I'm just renormalizing these Boltzmann factors here. Experimentally, what you need to do is basically just to compute this log of this ratio. And basically, all that you need to do is experimentally get what is the probability of measuring, let's say, you step in in an energy that appears in both histograms. And then basically, you compute the probability from one distribution and the probability of the other distribution. So this probability of beta E1, probability of beta E1 in beta prime. And then you do the analog for another different energy. So this energy is going to be a variable. Basically, you can pick any E1 and E2. And that's basically what you have here. So this is the delta E. So the nice observation of this construction, when you do this math, is basically that this quantity delta L, experimentally, as a function of delta E, should be a linear trend, if it is a Boltzmann type of distribution. And basically, the delta beta is simply giving, I know X because I know by how much I rescale the parameters. So I know absolutely everything. And basically, from the linear regression, I can compute the value of the effective temperature. So here is the algorithm, and here is actually some experimental data, how it looks. So actually, you see, when you sample from the D wave, let's say you get distribution number 1, distribution number 2. You can extract values of E1 and E2, basically when you have experimental data. And of course, I mean, the distribution is quite noisy. But in principle, that's a typical plot that you get from in any of these training algorithms. And basically, from the linear regression, you can extract the temperature. One thing actually to keep in mind is notice actually that these effective temperatures are usually much higher than the device temperature. The device temperature is 0.033. In this particular example, it's about 3 times the device temperature. And this is consistent with the quantum dynamics. With the open system dynamics, you're expected to have a much smaller gap and therefore a smaller temperature at the freeze-out point. So basically, this is all consistent, and this is what we observe. Here is actually the full-blown experimental data. So what we did is we trained a restricted Boltzmann machine for a particular data set that is used in computer science to do benchmarks. It's called the bars and stripes. And basically, you want to train a probabilistic graphical model that is capable of identifying or capable of generating bars and stripes. So you just feed the algorithm bars and stripes, and you hope that the algorithm can generate bars and stripes. So that's basically what you're doing. And then basically, here is the way. So what I want you to, so basically, the y-axis in this plot is the gold standard, is your metric, is the log likelihood. So the larger this value, the better the training. And what you see here is as you move along in the training iteration. So this is basically steps in this contrasted divergence updates. So as I mentioned, constructed divergence is actually an approach that you can do it approximately. Actually, the most standard one is you only do 1 Gibbs sampling, so it's contrasted divergence once, but you can do it contrasted divergence 100. Nobody does this because actually it's close to the exact result, and that would be extremely expensive. But here our purpose is not to show that we can beat the classical computer. Our approach is that we wanted to show that our method actually is getting very close, that you need to determine the effective temperature in order to get close to the exact results. That's basically our main point. So the dark green line here is basically the exact result of the training. And the one that you see here, the one that is the closest to that one is our approach if you estimate the effective temperatures at every single step in the iterations. The other approaches, let's say, for instance, like the orange, the red, or those are approaches, or even this light magenta, those ones are actually at fixed temperature. This is an assumption that has been taken in the community. And as I mentioned, between 2010 and 2015, there was no experimental reports on this, I think mainly because if you see actually the performance is very poorly if you make any of these assumptions. And this is understandable. I mean, you have an exponential factor where the temperature, if you are missing by a little bit the temperature, this is actually going to have critical effect in your training. So basically, here is just showing that actually our effective temperature, this red line is just to show you I'm determining the temperature at every single step in the iterations. Even if I give you the whole train of the 5,000 temperatures that I estimated and you calculate the average of that curve, you still don't reach actually the best performance that is if you estimate the temperature and you use it at every single iteration. So that's basically the main result. By the way, if I use the device temperature as a naive assumption, they actually, instead of learning, you actually de-learning is out of the scale. So in principle, and this is a naive assumption, shouldn't you do that? So here is actually another plot, just a zoom in one of these regions when you are doing the training. Here is actually how widely this temperature is varying as a function of the steps. And then basically what I'm showing here is notice that the fluctuations are easily of the order of 3 times the device temperature, and the temperature itself average is of the order of 3 times the device temperature. So here is actually why this needs to be determined very carefully if you really want to observe any good performance when you're using this type of approaches for training using, for instance, with devices or with any physical annealers. So this is actually an interesting result, because I think this is the very first demonstration of this paradigm of using hybrid quantum classical approach. So basically what we are showing here is that you can do CD1, that is very quick and dirty, it's cheap. You can do CD1 up to a certain point until you plateau. And then you say, OK, I'm done classically. That's the best that I can get. Notice that when you're doing the training classically, the classical computers, they don't know about temperature. They just know about weight and biases. They don't really have a sense of temperature. Everything is encoded in the weights and the biases. So basically, if you want to put this in a physical device, you need to translate that to H's and J's. And the only way to translate that is by using a temperature. If you don't know the temperature, you cannot restart from a certain point. What I'm showing here is that, again, if you use our approach for actually restart from there, estimating the temperature and restart, actually you can still outperform the CD1. So actually get better results by doing this hybrid quantum classical. And again, I'm showing here that if you use the naive assumption of just using the device temperature, actually the learning significantly drops. So actually, just to emphasize, and just putting this green line, just to emphasize that if you don't know the temperature, you cannot restart. And that's the only way to match classical and quantum processors. So I'm going to skip this because I think I'm out of time, almost out of time. But I just wanted to actually just give you this completely new results. And basically what you're seeing here is, again, our emphasis is in unsupervised learning. So basically, we're trying to, this is the most difficult paradigm of machine learning. So it's much more difficult than supervised learning. Here is an example where we took some digits. One of the rows is created by a human. The other one is created by the machine. So this is a Turing test for you guys. So how many of you think actually the top row was generated by the quantum machine? Just look at it. Just raise your hand. OK, got only one. How many of these you think actually was created by the human? They look human-like. Well, actually, human-like here, I mean, is there were digits, full digits, but they're coarse-grained just to make our experiments. But in principle, they both, I mean, one of them is human-like. So any takes? So basically, here's the results. Actually, the one on the top is the one created by the human. And the one at the bottom is created by the quantum machine. So basically, here's an example of number 1s, number 2, number 3, and number 4. They're directly taken from human digits, human, but just coarse-grained. But basically, this is the type. These samples were generated absolutely from a model that was trained with our approach. So not with our approach, sorry. Actually, this is a completely new different results that actually the nice thing is also is with this new theory that we developed for this particular model, in principle, you don't need to use that much effective temperature. You only use it at the end. So that's a nice thing, actually, about these new results. And with that, actually, I would like to conclude. Basically, the last results, and that's why I'm highlighting here, these are unpublished results. The nice thing is that one of the hardest difficulties we've seen in the conference is coping with the noise. And actually, if, as I mentioned, when you're trying to train a Boltzmann machine, you're working in the dual domain. Basically, you're not trying to get sample. You're really trying to assess what are the H's and the J's that best describe your data. The deliverable to the customer is the H's and J's. It's not the bit string. So basically, if you don't have control over the noise in the programmable parameters, therefore, you are in trouble. So basically, the nice thing about those results that I showed in the previous slide is that actually everything is worked more or less in a black box type of approach, where actually the device is used as a whole. Actually, everything is the noise and everything is built into account actually to get those results. So that's the only thing actually you can get this exciting progress there. And the nice thing also that I didn't mention in that result is that actually the results obtained in the previous actually go much more beyond the restricted Boltzmann machine. Actually, it's a model with a lot of connections. So actually, it's a very interesting, I think, approach. Actually, you see that easily you get in the training, like easily after 100 iterations instead of 5,000, you get a very boosted result. Of course, I mean, we're moving toward deep learning type of architectures. Some of the questions that are interesting is, how detrimental, someone was asking, how detrimental is if you're not sampling from Boltzmann? As you saw, actually, our indirect approach was to do the training, and as you see, actually was quite robust. You still managed to make progress. So I think it will depend, of course, from landscape to landscape, and I guess this will be dependent on the problem size. And some of the approaches, I mean, that we are taking as well is we're trying to address this question. I mean, this was work by Mohammed and by Evgeny about quantum Boltzmann machine. What can you do? What is the power of quantum annealing when you're actually working with the full quantum distribution? That's something that we think is very valuable and important for the next research directions. And another thing that, as I mentioned, we're just trying to understand at the moment, how can we even work with the device? I mean, actually, how can we make progress in seeing some significant training? And how do you actually think out of the box with these new quantum annealers? Now, I think the research direction I think that we're pushing is actually, can we answer this question? We had the analog question in quantum speedup. That's some work that we are doing with Hartmut, with Helmut, with everybody. I mean, I think this is a very important quantum speedup. We have the same type of question in machine learning is, can we actually, is quantum annealer a computational resource in this type of problems? Can it be? And actually, can we show some quantum supremacy, or can we show actually some significantly boosting of a speed up, just by showing, for instance, playing with highly connected models or playing with the actually using the noise in the device. And just finally, I wanted to advertise, we will have we're hosting a quantum annealing section in the NES AGU conference in San Francisco. So there will be an afternoon section. So please, contact me if you have any questions. And this is mostly for application type of related software packages and also applications. So that's it. Thank you very much.
Okay, we have time for a couple of questions.
So I am under impression that you need a sufficient overlap between histograms to calculate effective temperature. How do you ensure that, like these histograms are going to overlap, or what to choose as the scaling factor in there?
Yeah, basically, so in the paper itself, actually, we have a principled approach. Actually, we show exactly how the scaling should vary as a function of the training. Actually, so this is going to depend on the phase of the training that you're doing, and we have a principled approach. Basically, we keep the two distributions constant, the KL divergence. Instead of doing an X constant throughout the learning, you need to take into account that the distributions are changing. So that's one thing. In the paper, you can find the details. But in principle, just also, how do you do it in the first place? You need to experiment with that at the beginning, because there is still a hyperparameter that is the distance between the two distributions. And that you need to experiment a little bit. So it's a hyperparameter in the model. Yeah, so you just need to play a little bit with that.
Yeah, we have maybe time for one more quick question, if there is one. Oh, right.
Hey, so your variation over time in the effective temperature. From any given set of samples, there's of course some uncertainty in the estimation, and then. And also, I suppose the device temperature could be drifting. So, do you have any comment on the?
Yeah. So, I think it's a good question. So you can see actually in the plot itself that actually I think it is really hard. I mean, from what I talked to Trevor in the past, it's really hard that the device temperature is fluctuating three times actually the temperature itself. And the other thing is that you see error bars here actually. So this is the same training done many times, and actually this is the error bars that you see. And actually the green line is one of the realizations. But in principle, this experiment was done at least 5 times, and that's basically the spread from the same problem. So actually, this is just to show the robustness, and that this trend is not just one of the fluctuations in the estimation, because the estimation could be very noisy as well. So this is just to show that from realization to realization of the model, this is basically the error bars that you would get. And it doesn't cover the whole spectrum of the fluctuations itself.
Okay, well, I think we should probably leave any other questions till after we finish the session. So let's thank them again.